My name is Richard Zappula. I'm a 2010 and 2014 SMART cohort. So today we'll be talking about picking the right guidance, navigation, and control method for your situation. And so why is this important? It was identified that there's a big need for an increase in autonomous operations on space to pursue the next generation of missions. Here we have, I think, mostly iconic is the Falcon 9 first stage landing. This in itself is a huge guidance and control problem, right? You have a launch vehicle taking off from a fixed pad, and then after separation, somewhere downrange, it needs to retarget another point and maneuver to get back to its landing pad, which is either a fixed ground or on a barge in the middle of the ocean somewhere. And it only has very minimal propellant and a thrust to weight ratio of greater than 1, so it can't exactly hover. So it's essentially just crashing into the barge or the ground, more or less. So again, how do we pick the right guidance and control algorithm? And from this, can we develop a trade space? So what we did was utilizing the Naval Postgraduate School Poseidon testbed, which is just a 4x4 meter granite monolith, which is the largest for any university. We used these floating spacecraft simulators, which we could mimic, short duration on-orbit maneuvers for spacecraft in 2 dimensions. We used relevant test scenarios in order to extract critical information about these algorithms that we're testing. How robust are they to variations in measurements on where the obstacles are and what my states are. The path planning and replanning capabilities when you have both static, 1, 2, or moving obstacles. And then lastly, which is sort of the focal point, was this comparison metric, right? So we have, no good talks doesn't have equations, but basically we're looking at the 2 main critical points of any guidance and control algorithm, which is how much fuel am I using and how fast can I compute this? So here we just have a control effort that's normalized, and we can choose this normalizing factor kappa, and such that it becomes non-dimensional. And what's nice is by doing this, I was able to show that I can take a spacecraft and a car, or I can take a car, airplane, and turn it into a spacecraft, and I can use the same framework. So now I can apply this towards not just spacecraft, but autonomous vehicles, drones, multicopters, etc. So it's a lot more versatile. And then on the bottom here, we essentially have the sampling period of our guidance algorithm, whether it be 0.1 seconds, 1 second, 10 seconds, as well as the fastest rate of the computer. What's nice about this is that it becomes now a bounded trade space, right? So on the horizontal axis, we have our fuel efficiency, essentially. And then on the vertical axis, we have our computational efficiency. The computational efficiency is bounded by 1 on the bottom. And then here on the fuel efficiencies, it's bounded by both the fuel optimal, which is your minimum effort solution, as well as time optimal, which is your maximum effort solution. So your algorithm will essentially lie within this area.